On the first day of July, in the year 2025, a telescope perched on a remote mountaintop in the high desert of northern Chile noticed something that should not have been there. A faint smudge of light, a tiny, almost imperceptible speck drifting across a dense tapestry of ancient stars, the kind of thing that automated survey software flags, catalogs, and moves on from 100 times a night, every single night, all year long. The machinery of modern astronomy is built to process noise, to separate the meaningful from the meaningless, to sift through the cosmic static and find the signals that matter. But this signal was different, because this particular speck of light was not orbiting our sun. It was not looping around Jupiter on some lazy, gravitationally predictable arc. It was not tumbling slowly through the asteroid belt on an elliptical path that astronomers had catalogued and filed away decades ago. It was not following any trajectory that belonged to our solar system at all. This object was falling through our neighborhood from the outside. It was screaming through the void at over 220,000 kilometers per hour, more than 60 kilometers every single second, and it showed absolutely no sign of slowing down. Its path was not an ellipse, it was not a circle, it was a hyperbola, an open curve, a one-way ticket. This thing was passing through, and it was never, ever coming back. Within 48 hours of the initial detection, observatories on 4 continents had confirmed what the raw trajectory data was already screaming at the top of its lungs. This was an interstellar object, a visitor beyond the boundary of our star system, a traveler from the abyss between suns, and it was only the 3rd such object ever recorded in the entire history of human civilization. They designated it 3I Antillas. The 3I means third interstellar. The Antillas refers to the telescope system that found it, the Asteroid Terrestrial Impact Last Alert System, a NASA-funded robotic survey telescopes originally designed not to find interstellar tourists, but to spot incoming asteroids that might pose a threat to life on Earth, a planetary defense system that, almost by accident, became humanity's first line of detection for visitors from other star systems. And from the moment 3I Antillas appeared in our data, from the very first confirmed observation, nothing about this object made sense.
Now, I want to be very careful here, very precise, because when you tell a story like this, a story involving an object from another star, anomalous behavior, and the word spaceship, it's easy to slide into sensationalism. It's easy to let the excitement run ahead of the evidence. And that's not what we're going to do. What we are going to do is look at the facts, all of them. The comfortable ones and the uncomfortable ones. The observations that fit neatly into our existing models and the observations that absolutely do not. We're going to listen to what the scientific mainstream says, and we're going to listen to what the scientific fringe says. And we're going to let you, the viewer, the thinker, the curious mind watching this in the quiet dark, decide for yourself what you believe. Because the truth is, nobody knows what 3I Iota Atlas really is. Not with certainty, not yet, maybe not ever. The scientific consensus, the mainstream, peer-reviewed, institutionally endorsed position held by the vast majority of planetary scientists, cometary experts, and observational astronomers, is that 3I Iota Atlas is a comet. An unusual comet, certainly, an interstellar comet that formed around another star system, was gravitationally ejected from that system billions of years ago, drifted through the incomprehensible emptiness of interstellar space for eons, and then, by sheer cosmic chance, stumbled into the gravitational embrace of our sun and passed through our little corner of the Milky Way. Under this interpretation, the anomalies, and there are many anomalies, we'll get to all of them, are the expected result of studying an object type we've only ever seen 3 times. We don't have enough data to know what's normal for an interstellar comet, so of course it looks weird. Everything looks weird the first few times you see it. That explanation may very well be correct. It is, by the standard measures of scientific reasoning, the most parsimonious explanation, the simplest one that fits the data. Occam's razor wielded with institutional confidence. But here's what I want you to understand about science. Real science, not the sanitized textbook version where knowledge progresses in neat, linear steps from ignorance to understanding, but the actual, messy, combative, deeply human practice of trying to figure out what's true about the universe. Science does not progress by accepting the comfortable answer. Science progresses by paying obsessive, meticulous, almost unreasonable attention to the anomalies, to the things that don't fit, to the data points that make the existing model creak and groan under the strain of explanation.
Every major revolution in science, every single one, began with an anomaly that the mainstream tried to explain away. The orbit of Mercury didn't fit Newtonian gravity. The black-body radiation spectrum didn't match classical thermodynamics. The arrangement of continents looked suspiciously like puzzle pieces. The cosmic microwave background sounded like static in a telephone receiver. Anomalies are not bugs in the system of scientific knowledge. They are features. They are the universe's way of tapping us on the shoulder and saying, "Pay attention, you're missing something." And 3I-Atlas has produced anomalies, a lot of them. 22 to be exact. At least that's the count as of March 2026, compiled and cataloged by Avi Loeb, the former chair of the astronomy department at Harvard University, the founding director of Harvard's Black Hole Initiative, the director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics, and currently the head of the Galileo Project, an initiative dedicated to the scientific search for evidence of extraterrestrial technological artifacts. Loeb is, depending on whom you ask, either a visionary scientist willing to ask the questions everyone else is too afraid to ask, or a publicity-seeking provocateur who has weaponized his Harvard credentials to promote a hypothesis that virtually no planetary scientist takes seriously. The truth, as usual, is more complicated than either caricature. What's undeniable is this: 22 separate observations of 3I-Atlas deviate from the expected behavior of a natural interstellar comet. 22 data points that make the "it's just a comet" explanation work harder than it should have to. Does that mean it's a spaceship? Not necessarily, not even probably. But it means we need to have a serious, rigorous, intellectually honest conversation about what this object is and what it isn't. Because dismissing the anomalies without investigation is not science. It's dogma wearing a lab coat. So settle in. This is going to be a long one. And it should be. Because when the universe hands you something like 3I-Atlas, something genuinely unprecedented, something that has mobilized every major telescope on Earth and in space, something that has triggered the largest coordinated observational campaign in the history of astronomy, you don't rush through it. You savor every detail. You examine every angle. You let the evidence speak, even when it whispers things you weren't expecting to hear. Let's begin. To understand why 3I/ATLS is so remarkable, you first need to understand how vanishingly rare interstellar objects are, or at least how rarely we detect them. Before 2017, we had never confirmed the existence of a single object passing through our solar system from interstellar space, not one. In the entire history of telescopic astronomy, stretching back over 4 centuries to Galileo peering through his crude instrument at the moons of Jupiter, every single comet, asteroid, meteor, and space rock we had ever observed was a local. Something born in our solar system, orbiting our sun, part of our cosmic family. We knew, theoretically, that interstellar objects must exist.
The process of planetary formation is messy, violent, and wasteful. When giant planets migrate through a young solar system, they gravitationally scatter enormous quantities of smaller material, comets, asteroids, planetesimals, flinging them outward at speeds high enough to escape the star's gravity entirely. Computer simulations predicted that every star system in the galaxy should eject billions of such objects over its lifetime. The Milky Way should be absolutely teeming with interstellar debris, trillions upon trillions of frozen, ancient bodies drifting silently between the stars. But we'd never seen one. The problem was detection. These objects are small, dark, cold, and unimaginably far away. Even when they pass through our solar system, they move fast, too fast to be gravitationally captured, too fast to linger, and unless they happen to pass relatively close to the sun and light up with a coma and tail like a comet, they're essentially invisible. Then, on October 19, 2017, everything changed. The Pan-STARRS 1 telescope in Hawaii detected an object that had already passed through its closest approach to the Sun and was heading back out toward interstellar space. It was designated 1I/Oumuamua, the first confirmed interstellar visitor. Oumuamua is a Hawaiian word meaning roughly a messenger from afar arriving first. And it was deeply, profoundly weird. Oumuamua was small, maybe a few hundred meters across. It had no coma, no tail, no visible outgassing. It reflected sunlight in a way that suggested an extremely elongated shape. Some estimates put its aspect ratio to 10:1, like a cosmic cigar or a pancake, depending on which model you preferred. Most disturbingly, it exhibited a small but measurable non-gravitational acceleration. It was speeding up slightly as it moved away from the sun, as if something was pushing it. For a comet, non-gravitational acceleration is explained by outgassing. As volatile ices sublimate, the escaping gas acts like a gentle rocket thrust. But Oumuamua showed no evidence of outgassing, no coma, no tail, no spectral signatures of gas emission. Whatever was accelerating it, it wasn't behaving like any comet we'd ever seen. This is when Avi Loeb entered the picture. In 2018, Loeb and his colleague Shmuel Bialy published a paper suggesting that Oumuamua's acceleration could be explained if the object was a thin, flat, artificial structure, a solar sail, being pushed by the pressure of sunlight, an artifact, a piece of alien technology, whether active or defunct, drifting through the galaxy. The paper was met with a firestorm of criticism from the planetary science community. The consensus position was that Oumuamua was most likely a natural object, perhaps a nitrogen ice fragment from a Pluto-like world in another star system, whose outgassing was too diffuse to detect. The solar sail hypothesis was dismissed as extraordinary speculation, unsupported by the evidence. Loeb, to his credit, didn't back down. He wrote a best-selling book about it, he founded the Galileo Project, and he kept watching the sky. 2 years later, in August 2019, amateur astronomer Gennady Borisov discovered the second interstellar object, 2I Borisov. This one was more straightforward. It had a coma. It had a tail. It outgassed water and carbon monoxide. It looked, in almost every respect, like a perfectly normal comet, just one that happened to be from another star system. 2I Borisov was reassuring. It showed that interstellar comets could behave pretty much like our own comets. It suggested that the chemistry of other stellar systems might not be radically different from ours. It was a data point in favor of cosmic normalcy. And then, 6 years later, 3I ATLS arrived, and normalcy went out the window. Let's reconstruct the discovery in detail, because the sequence matters. The ATLAS telescope in Rio Hurtado, Chile,
one of 4 Atlas stations scattered around the globe, designed to scan the sky every 2 nights looking for dangerous near-Earth objects, captured its first images of the object on July 1, 2025 at 05:15:11 Universal Time. The observation was reported to the Minor Planet Center, the International Clearinghouse for Solar System Body Tracking, within hours. At the time of discovery, 3I ATLS was approximately 670 million kilometers from the Sun, within the orbit of Jupiter, but still far from the inner solar system. It was faint, magnitude 17.8, invisible to the naked eye, invisible to binoculars, invisible to all but the most powerful amateur telescopes, a ghost in the data. But even in those first images, something was off. The object's motion across the sky was too fast for its distance. Its trajectory was curving the wrong way. The preliminary orbital calculations didn't close. The orbit wasn't an ellipse, it was a hyperbola. Within hours, astronomers around the world began digging through archival data, looking for pre-discovery observations. They found them. The Zwicky Transient Observatory at Palomar Observatory in California had captured 3I ATLS as early as June 14th, more than 2 weeks before the official discovery. Atlas's own archives had images going back to June 5th. The interstellar visitor had been in our data for nearly a month before anyone realized it was interstellar. Amateur astronomer Sam Dean noted that the reason for the late detection was almost poetic. 3I ATLS had been passing in front of the dense star fields of the galactic center in the constellation Sagittarius. Against that backdrop of millions of stars, one more faint moving speck was easy to miss. The interstellar visitor had hidden in plain sight, camouflaged by the galaxy itself. By July 2nd, the interstellar nature of the object was confirmed. The European Southern Observatory's Very Large Telescope in Chile detected a faint elongated coma, a fuzzy envelope of gas and dust surrounding the nucleus. 3I ATLS was outgassing. It was behaving, at least superficially, like a comet. On July 21st, the Hubble Space Telescope captured its first image of the visitor, and that image was stunning. It showed a teardrop-shaped cocoon of dust billowing away from a tiny, unresolved nucleus. The solid core of 3I ATLS was too small for even Hubble to see as anything more than a point of light, but the surrounding envelope of material was clearly visible, its tendrils stretching out into the vacuum. Because Hubble had to track the fast-moving object, the background stars were smeared into streaks in the exposure, creating an image that looked almost cinematic. An interstellar traveler, frozen in a moment of transit, surrounded by its own atmosphere, with the stars of our galaxy streaking past like hyperspace lines in a science fiction film.
It was real. It was here, and the entire astronomical establishment mobilized to study it. NASA assembled a fleet. Hubble, the James Webb Space Telescope, TESS, the Transiting Exoplanet Survey Satellite, the Swift Gamma Ray Observatory, SphereX, the spectrophotometer for the history of the universe, epoch of reionization, and ICES Explorer, a space telescope launched in early 2025 specifically designed to survey the sky in near-infrared light, the Perseverance Mars Rover, Mars Reconnaissance Orbiter, MAVEN, Europa Clipper, Lucy, Psyche, Parker Solar Probe, Punch, SOHO. ESA contributed Mars Express, the ExoMars Trace Gas Observatory, and the Jupiter Icy Moons Explorer, JUICE. China's Tianwen-1 Mars Orbiter captured its own images. Ground-based observatories from Gemini to ALMA to the Very Large Telescope to the Canada-France-Hawaii Telescope all pointed their instruments at the incoming visitor. It was, without exaggeration, the largest coordinated astronomical observation campaign in human history. More instruments were trained on 3I Atlas than had ever been simultaneously aimed at any single solar system object. Every wavelength, from radio to X-ray, every technique, from spectroscopy to polarimetry to astrometry. The universe had sent us a message, and we were determined to read every word. Let's talk about the trajectory, because the path of 3I Atlas through our solar system is where the story starts getting genuinely uncomfortable for the "it's just a comet" explanation. When you trace the inbound trajectory of 3I Atlas backward through space, it came from the general direction of the constellation Sagittarius. Not just anywhere in Sagittarius, from a region near the center of our galaxy, the Milky Way's core, the densest, most star-rich region of the entire galactic disk. Now, interstellar objects can, in principle, arrive from any direction. The sky is a sphere of 41,253 square degrees, and an object drifting through the galaxy could approach our solar system from any point on that sphere. There's no preferred direction, no cosmic highway, just random vectors in three-dimensional space. But 3I Atlas didn't arrive randomly. Its trajectory was retrograde, meaning it was moving in the opposite direction to the planets around the Sun. That's unusual, but not unprecedented. Roughly half of all possible trajectories would be retrograde. What's truly unusual is the inclination. The orbit of 3I Atlas was tilted just 5 degrees from the ecliptic plane, the flat disk along which all 8 planets orbit the Sun. 5 degrees, out of a possible 180. The ecliptic plane is a razor-thin slice of the celestial sphere. Imagine the planet's orbits as a dinner plate and the full sky as a basketball. The ecliptic plane is a cross-section through the middle of that basketball, an infinitesimally thin line, cosmically speaking. The probability that an interstellar object would align with the ecliptic to within 5 degrees is approximately 0.2%, about 1 in 500. And keep in mind, the Milky Way's disk is tilted about 60 degrees relative to the ecliptic, so there's no physical reason for an interstellar object to preferentially align in the ecliptic plane, unless its trajectory was not random. Loeb and his colleagues published a detailed statistical analysis of this alignment. They noted that the retrograde near-ecliptic trajectory of 3I Atlas brought it remarkably close to 3 different planets, Mars, Venus, and Jupiter. Not just close in the sense of passing through the same region of space, close in both space and time. The timing of its arrival was such that each planetary encounter happened near the closest possible approach, as if the trajectory had been optimized.
They calculated the probability of this multi-planet alignment occurring by chance. Their result, 0.005%, 1 in 20,000. Now, I want to be fair to the counter-argument here. Planetary scientists point out that low-probability events happen all the time. If you flip a coin 20 times and get 17 heads, that's a 1 in 3,000 event, but it doesn't mean the coin is rigged. It means you got lucky, or unlucky, depending on how you bet. The Milky Way has been producing interstellar objects for over 10 billion years. Trillions of them have passed through our solar system over its 4.6 billion year history. We've only detected 3. We have no idea what the statistical distribution of trajectories looks like for the underlying population. It's entirely possible that 3I/Atlas hit an improbable trajectory purely by chance, and we just happened to be the ones watching when it did. But here's what bugs the skeptics of the skeptics. It's not just the alignment. It's the combination of the alignment with everything else.
Because the trajectory doesn't exist in isolation, it exists alongside the antitail and the nickel ratio and the brightness anomaly and the jet symmetry and all the other things we're about to discuss. And at some point, the accumulation of improbable coincidences starts to feel less like luck and more like a signal. Whether that signal is natural or artificial, that's the question. Let me walk you through the specific planetary encounters because each one tells its own story. Mars, October 3rd, 2025. 3I/Atlas passed Mars at a distance of just 29 million kilometers, 0.194 astronomical units. That's close. Astonishingly close for an interstellar object, close enough that multiple spacecraft orbiting Mars were able to image it directly. ESA's Trace Gas Orbiter turned its CASSI camera toward the incoming visitor and captured clear images. Mars Express attempted the same but came up empty, probably due to shorter exposure times. China's Tianwen-1 orbiter also managed to photograph the object. NASA's Mars Reconnaissance Orbiter took images with its HiRISE camera, but the data wasn't publicly released. NASA was dealing with institutional disruptions at the time. But perhaps the most extraordinary observation came from the surface of Mars itself. NASA's Perseverance rover, a car-sized robot sitting in Jezero crater, 29 million kilometers from the nearest interstellar object, pointed its camera skyward and captured images of 3I/Atlas as it streaked past. Let me repeat that because the magnitude of this moment deserves a pause. A machine built by human beings sitting on the surface of another planet in our solar system looked up into the Martian sky and photographed an object that was born around another star in another part of the galaxy billions of years ago. 3 layers of cosmic separation, human to Mars to interstellar space, bridged in a single photograph. This is the kind of moment that in a rational world would make the front page of every newspaper on Earth. A moment that collapses the distances between worlds and reminds us of the staggering improbability of our own existence. The fact that it was treated as a footnote, buried beneath politics and celebrity gossip and the infinite scroll of social media, tells you something about the age we live in. We have become so accustomed to miracles that we've forgotten to be astonished.
After Mars, 3I/Atlas continued inward. It passed behind the Sun, entering what astronomers call solar conjunction, where its angular separation from the Sun dropped too low for ground-based telescopes to observe it safely. This happened in late October 2025, right around perihelion. Perihelion, the closest approach to the Sun. October 29th, 2025. At perihelion, 3I/Atlas was about 203 million kilometers from the Sun, 1.36 astronomical units, just inside the orbit of Mars. Not especially close by cometary standards, many solar system comets pass far closer to the Sun, some plunging inside Mercury's orbit. But for an interstellar object moving at such extreme velocity, this was significant. The solar heating was intense enough to drive vigorous sublimation of volatiles from the surface and subsurface of the nucleus. And it was during this perihelion passage that things started getting really strange. During the weeks immediately before and after perihelion, when 3I/Atlas was hidden behind the Sun's glare from Earth-based telescopes, ESA's SOHO spacecraft, the Solar and Heliospheric Observatory, a joint ESA-NASA mission parked at the L1 Lagrange point between Earth and the Sun, managed to detect the object in its coronagraph images. SOHO was designed to study the Sun's outer atmosphere, and its wide-field cameras routinely photograph comets that stray too close to the Sun.
3I Atlas was expected to be too faint for SOHO to see, but careful image processing, stacking multiple exposures and applying sophisticated noise reduction revealed the interstellar visitor gliding through the solar corona's neighborhood. Meanwhile, the spacecraft that had the best view of 3I Atlas during perihelion was ESA's Jupiter Icy Moons Explorer, JUICE. Launched in April 2023 and en route to Jupiter, JUICE happened to be in the inner solar system at the time, and its trajectory brought it within about 64 million kilometers of 3I Atlas in early November 2025. JUICE observed the object with multiple instruments, cameras, spectrometers, and a particle sensor. But there was a catch. JUICE was traveling through the inner solar system, where solar heating was intense, and it was using its main high-gain antenna as a heat shield, literally pointing it at the sun to protect its instruments. Data transmission had to go through a smaller, slower, medium-gain antenna. The result, JUICE could observe 3I Atlas, but it couldn't send most of the data home until later. A quarter of a navigation camera image was quickly downloaded and revealed an actively outgassing comet with a clear tail and structure in the coma. But the rest of the data, the detailed spectroscopic and imaging observations, didn't arrive on Earth until February 2026. When that data finally came through, instrument teams began the painstaking process of analysis, and what they found added new chapters to an already extraordinary story. But before we get to the detailed anomalies, and we will get to all of them, I promise, let's establish the physical picture. What do we actually know about 3I Atlas as an object? The nucleus, the solid, icy body at the heart of 3I-ATLS, is small enough that even the Hubble Space Telescope can't dissolve its surface. Hubble can see the coma, the dust tail, the jets, but the nucleus itself appears as a point source, a single bright pixel buried in the glare of its own outgassing. Based on Hubble observations from August 2025, astronomers estimated the diameter of the nucleus to be somewhere between 440 meters, about the length of 4 football fields, and 5.6 kilometers, or about 3.5 miles. That's an enormous range of uncertainty, driven by assumptions about the object's albedo, how reflective its surface is, and the brightness contribution of the surrounding coma. Later analysis, based on the measured non-gravitational acceleration and the estimated mass loss rate, narrowed the estimate. The most likely value appears to be around 2.6 kilometers, roughly 1.5 miles across, about the size of a large mountain, or, as various media outlets breathlessly reported, approximately the size of Manhattan. For comparison, 1I-Oumuamua was estimated at roughly 100 to 400 meters. 2I-Borisov was about 500 to 1 kilometer. 3I-ATLS is significantly larger than either of its predecessors. And this matters because in the population statistics of small bodies, whether in our solar system or in interstellar space, size distributions follow power laws. Smaller objects are exponentially more common than larger ones. For every object the size of 3I-ATLS, there should be thousands, perhaps millions of smaller interstellar bodies passing through our solar system at any given time. But we haven't detected those smaller bodies. Our surveys are biased toward larger, brighter objects, so the fact that the third interstellar object we've ever found is this big tells us one of two things. Either 3I-ATLS is a statistical outlier, the equivalent of finding a whale the first time you drop a net in the ocean, or the population of interstellar objects is very different from what our models predict. Loeb and his colleagues went further. They calculated the implied number density of 3I-ATLS-sized interstellar objects based on our detection rate and compared it to the mass budget available in protoplanetary disks around low metallicity stars. Their conclusion, the implied population exceeds the available mass reservoir by orders of magnitude. In plain language, there isn't enough raw material in the galaxy's star-forming regions to account for as many large interstellar objects as our detection of 3I-ATLS would imply. Either we got spectacularly lucky in finding one, or there's something fundamentally wrong with our understanding of how these objects are produced, or 3I-ATLS is not a typical member of the interstellar small body population. The speed of 3I-ATLS added another dimension to the puzzle. At discovery, it was moving at about 221,000 kilometers per hour, roughly 60 kilometers per second. As it fell deeper into the sun's gravitational well, it accelerated to about 246,000 kilometers per hour, 68 kilometers per second, at perihelion. That makes it the fastest interstellar visitor we've ever clocked. For context, the Voyager 1 spacecraft, after getting gravity assists from both Jupiter and Saturn and having been traveling for nearly half a century, is currently doing about 17 kilometers per second. 3I-ATLS entered our solar system at more than 3 times that speed, under its own momentum, with no engine. When it leaves our solar system, when it finally escapes the sun's gravity and returns to interstellar space, it will be traveling at the same speed it arrived, 60 kilometers per second. Because gravity is a conservative force. What it gives during approach, it takes back during departure. At 60 kilometers per second, 3I-ATLS will cover the distance between Earth and the Sun in about a month. It will reach the inner edge of the Oort cloud, the vast spherical shell of icy bodies that marks the outermost boundary of the Sun's gravitational influence, about 2,000 astronomical units away, around the year 2189. It will reach the outer edge of the Oort cloud in about 8,000 years. And then it will be gone, back into the void between stars, adrift in the galaxy for billions more years, until perhaps someday, around some distant star, another civilization detects a faint speck of light moving too fast across their sky and wonders where it came from. Unless they already know. Now let's get to the anomalies, all of them, one by one. I've organized these roughly thematically: trajectory anomalies first, then physical and structural anomalies, then chemical and spectroscopic anomalies, then observational puzzles. But understand that in reality, these categories bleed into each other. The trajectory affects the chemistry, affects the physics, affects the observation. It's all one interconnected web of strangeness. Trajectory and orbital anomalies. Anomaly 1, the ecliptic alignment. We've already discussed this, but it bears repeating in the context of the full list. The retrograde trajectory of 3I-Atlas is aligned to within 5 degrees of the ecliptic plane, the orbital plane of the planets around the Sun. The Milky Way's disk is misaligned with the ecliptic by about 60 degrees. There is no known physical mechanism that would preferentially funnel interstellar objects into the ecliptic plane. The probability of this alignment occurring by chance is approximately 0.2%. For a natural interstellar comet, this alignment is surprising but not impossible. For an object that was deliberately targeted at the solar system, alignment with the ecliptic would make perfect sense. It maximizes the number of close encounters with planets. Anomaly 2, the multi-planet approach. 3I-Atlas didn't just arrive in the ecliptic plane, it arrived at a time and along a path that produced close approaches to 3 major planets: Mars, 29 million kilometers on October 3, 2025, Venus, 97 million kilometers on November 3, 2025, and Jupiter, 53.6 million kilometers on March 16, 2026. NASA's Jet Propulsion Laboratory, using orbital data from over 230 observatories worldwide, including the measured non-gravitational acceleration of the object, calculated that 3I-Atlas would pass Jupiter at a minimum distance of 53.56 million kilometers. with an error measurement of plus or minus 0.06 million kilometers. The hill radius and the closest approach distance are identical within 1 standard deviation of the uncertainty. Let me translate that into something visceral. Imagine you're standing on a football field. The goal line on one end represents 0 kilometers, the center of Jupiter. The goal line on the other end represents 100 million kilometers. Jupiter's hill radius, the boundary of its gravitational dominance, is at the 53.5 yard line, and 3I Atlas passed at the 53.56 yard line, with an error bar of about 2 inches. For a natural comet following a gravitationally determined path through the solar system, this is a coincidence, an eerie one but ultimately meaningless. The hill radius has no physical significance for an object moving at 66 kilometers per second relative to Jupiter. At that speed, Jupiter's gravity can deflect the trajectory slightly but cannot capture the object. But for a hypothetical spacecraft designed to deposit probes within Jupiter's gravitational sphere of influence, arriving at exactly the hill radius would be profoundly significant. It would be the ideal deployment distance, close enough for deployed objects to be gravitationally bound to Jupiter, but far enough to avoid the intense radiation environment of the inner magnetosphere. Loeb proposed exactly this scenario. He suggested that if 3I Barricini Atlas were an artificial object, what he calls a mothership, it could deploy technological devices within Jupiter's hill sphere during the flyby. These devices would need to decelerate from 66 kilometers per second, the speed of 3I Barricini Atlas relative to Jupiter, to a few kilometers per second, orbital speed around Jupiter, which would require significant thrust. But once deployed, they could orbit Jupiter indefinitely. He further suggested that future imaging missions, Juno, JUICE, Europa Clipper, should watch for the appearance of unfamiliar small objects in Jovian orbit after March 2026, new satellites of Jupiter that we didn't put there. Is this science fiction? Maybe. But it's falsifiable science fiction. It makes a specific prediction that can be tested by observation, and that's the line between speculation and science. Anomaly 4, the arrival direction and the WOW signal. On August 15, 1977, the Big Ear radio telescope at Ohio State University detected a powerful narrowband radio signal at 1420 MHz, the hyperfine transition frequency of neutral hydrogen, and the frequency most commonly discussed as a logical channel for interstellar communication. The signal lasted 72 seconds, corresponding to the transit time of a celestial source through the telescope's beam. It was so striking that astronomer Jerry Imons circled the alphanumeric sequence on the printout and wrote a single word in the margin: "Wow." The WOW signal has never been satisfactorily explained. Various hypotheses have been proposed: a satellite reflection, a comet releasing hydrogen gas, a magnetar flare illuminating an interstellar hydrogen cloud, but none has been confirmed, and the signal has never been detected again despite extensive follow-up observations. The WOW signal originated from the sky coordinates of right ascension 19 hours 25 minutes, declination minus 27 degrees, the direction of Sagittarius. When Loeb calculated the position of 3I Barricini Atlas in August 1977, backtracing its trajectory using the precise orbital parameters determined from months of modern observation, he found that the object would have been roughly 600 astronomical units from the Sun, still in interstellar space but within the outer reaches of the Sun's gravitational influence, and its position in the sky would have been at right ascension 19 hours 40 minutes, declination minus 19 degrees. The angular separation, approximately 9 degrees. This is not proof of anything. 9 degrees is still a significant angular distance, roughly 18 times the apparent diameter of the full moon. and the wow signal has multiple proposed natural explanations, but the coincidence in direction combined with the coincidence in frequency, 1420 MHz, the hydrogen line, exactly the frequency you'd choose for interstellar communication, combined with the fact that 3I Baracini Atlas is confirmed to have come from that general direction of the sky. It's the kind of coincidence that makes the hair on the back of your neck stand up, even if you know rationally that it's probably meaningless. Physical and structural anomalies. Anomaly 5, the anti-tail. This is one of the most visually striking and scientifically puzzling features of 3I Baracini Atlas.
Comets develop tails because solar radiation pressure and the solar wind, the stream of charged particles constantly flowing outward from the sun at 400 to 800 kilometers per second, push dust and ionized gas away from the nucleus. This creates the characteristic tails that make comets so photogenic, a broad, curved dust tail and a narrow, straight ion tail, both pointing generally away from the sun. Some comets develop what appears to be an anti-tail, a spike of material pointing toward the sun rather than away from it. In most cases, this is a perspective effect. When Earth, the comet, and the sun are arranged in certain geometries, the three-dimensional shape of the dust tail can project onto the sky in a way that creates the illusion of a sunward-pointing feature. It's not actually material moving toward the sun, it's the line-of-sight angle playing tricks. But the anti-tail of 3I-ATLS was not a perspective effect. Analysis of high-resolution Hubble Space Telescope images combined with careful geometric modeling of the Earth-Comet-Sun geometry showed that 3I-ATLS possessed a genuine physical jet of material directed toward the Sun. Before perihelion, this sunward jet appeared as a collimated beam, narrow and focused, extending to distances of hundreds of thousands of kilometers from the nucleus. The jet was approximately 10 times longer than it was wide. No known solar system comet has ever produced a physical sunward jet of this length and collimation. Ever. In the entire history of cometary science. Individual comets have been observed with sunward-facing active regions that produce localized jets toward the sun, but these are typically short-lived, low collimation features that disperse quickly. What 3I-ATLS displayed was sustained, coherent, and extended. After perihelion, the picture became even more complex. Hubble images processed with the Larsen-Sechenina rotational gradient filter, a technique that enhances fine structures by subtracting a rotated version of the image from itself, revealed a symmetric structure around the nucleus, a sunward anti-tail plus 3 additional jets equally spaced at 120-degree intervals. We'll discuss the 3-jet symmetry separately, but note that the anti-tail was part of a larger geometrically organized system, not a random outgassing feature, a structured pattern. Loeb proposed that for a technological object, a directed beam of particles aimed at the sun could serve a functional purpose, deflecting the incoming solar wind. The solar wind hits objects in the inner solar system at relative speeds of around 500 kilometers per second. For a spacecraft, especially one with sensitive surface equipment, shielding against this bombardment would be essential. A beam of exhaust material directed sunward could create a magnetic draping structure or a plasma buffer that diverts the solar wind around the object, much like a bow shock protects a planet's magnetosphere. Is there a natural explanation? Possibly. One suggestion involves a sunward-facing active region on the nucleus that happens to point at the sun due to the object's rotation state.
If 3I-ATLS's rotation axis were nearly aligned with the Sun-comet direction, and there's evidence from the wobble analysis that it is, then a persistent active region could produce a sustained sunward jet. But this explanation requires a coincidental alignment of the rotation axis with the Sun direction, yet another low-probability geometric arrangement on top of all the others. Anomaly 6, the dust veil.
Hubble images showed that 3I-ATLS was surrounded by a cocoon of dust, a spherical or near-spherical envelope of fine particles enveloping the nucleus. This is not unusual for an active comet. Outgassing pushes dust off the surface, and some of it hangs around the nucleus before being swept away by solar radiation pressure. What was unusual was the column density of this dust. Analysis suggested that the total amount of dust surrounding 3I-ATLS was precisely sufficient to attenuate a significant fraction of incoming sunlight before it reached the nucleus surface. The dust veil was essentially a natural sunshade, thin enough to still allow some light through, but thick enough to meaningfully reduce the thermal load on the nucleus. If you were designing a thermal protection system for a spacecraft passing through the inner solar system, a deployable parasol of microscopic particles released to shade the hull from solar radiation, you would aim for approximately this column density. The counterargument: comets naturally produce dust halos, and the column density is determined by the outgassing rate, particle size distribution, and solar radiation pressure. There's no need to invoke intentional design. The dust is doing what dust does. True, but the coincidence between the observed column density and the functionally optimal column density for thermal protection is notable. Anomaly 7, the 3 symmetric jets. This is the anomaly that made planetary scientists lean forward in their chairs. Post-perihelion images from Hubble, taken on December 27, 2025, and processed using the Larsen-Sekanina rotational gradient filter, revealed 3 distinct jets of material emanating from the nucleus of 3I-ATLS. The jets were equally spaced, separated by 120 degrees around the circumference of the nucleus, and appeared approximately equal in intensity and extent. In cometary science, jets are common. When a comet's nucleus rotates, different regions of its surface cycle through sunlight and shadow. Areas rich with volatile ices, the active regions, sublimate when heated, producing geysers of gas and entrained dust. These jets can be highly directional, and they rotate with the nucleus, creating corkscrew-shaped patterns in the coma. But the key word is randomly. Active regions on a comet's surface are determined by the uneven distribution of volatile ices, which is itself determined by the chaotic history of the body's formation and evolution. There's no reason to expect any particular symmetry in the arrangement of active regions. 3 jets, equally spaced at 120-degree intervals, represents a 3-fold rotational symmetry. This is the kind of symmetry you see in engineered objects: 3-engine rocket configurations, 3-blade propellers, 3-legged stabilizing structures. It is not the kind of symmetry you expect from a randomly formed natural body with an irregular, heterogeneous surface. Now, to be fair, it's possible for a natural body to develop a pattern of active regions that happens to approximate a symmetric arrangement. If the nucleus has 3 large deposits of volatile ice distributed roughly equally around its equator, perhaps due to some coincidence of its formation history, then you'd get 3 jets roughly 120 degrees apart. But roughly is doing a lot of work in that sentence. The observed jet separation was close to exactly 120 degrees, not approximately, not sort of, close to exact. And the jets exhibited periodic wobbling,
precession, suggesting that the nucleus was rotating around an axis that itself was slowly changing orientation. The wobble was regular, predictable, and consistent with a rigid body undergoing torque-free precession, the kind of rotation you see in a well-balanced spinning object, not a lumpy, irregular chunk of rock and ice. Anomaly 8. The wobble and spin axis alignment. We just mentioned the precession of the nucleus. Let's dig deeper. Detailed analysis of the jet morphology over time, how the jets changed shape, orientation, and intensity from one Hubble observation to the next, revealed the researchers to constrain the rotation state of 3I-ATLS. The nucleus appeared to be spinning with a rotation period of several hours, and the spin axis was precessing, wobbling like a slowly tilting top, with a period of roughly a day or two. What's striking is the orientation of the spin axis. It was nearly aligned with the direction from the nucleus to the Sun. For a random comet, the spin axis can point in any direction. There's no physical mechanism during interstellar travel that would preferentially align a body's rotation axis with the Sun upon arrival. The alignment must have occurred either by extraordinary coincidence or through some dynamical process during the solar encounter. One possibility, the outgassing torques experienced by 3I-ATLS as it approached the Sun gradually reoriented its spin axis toward a Sun-pointing direction. This is physically plausible, but requires a specific distribution of active regions, predominantly sunward-facing, which itself requires explanation. And it doesn't account for the precise degree of alignment observed, which was tighter than simple torque models predict.